So, in this video, I'm going to try to help you understand why the frost formed on the popsicle. So, in order to do that, I had you watch a video that showed an aluminum can placed with salt and ice in a room temperature environment. And after a short amount of time, frost formed on the outside of the aluminum can. So, why did that happen? So, to begin explaining, I drew out the molecules that would be found in the aluminum can if I had microscope eyes. The aluminum can is a solid, and so therefore, molecules would be close together and vibrating in place. Next, I did a zoom in on the air, and the air is made up of a bunch of different things, but in this case, I just drew the air molecules generally as orange, but then I was intentional about putting the water vapor molecules as blue. So showing that water vapor in our air is going to be a significant player in where the frost comes from. The next thing I did was draw an arrow showing that ice with salt had been added to the inside of the aluminum can. And the reason salt was added is that when salt and ice are combined, it lowers the freezing point of the salt, of the ice. So, in other words, one of the physical properties of water is that it freezes at 32 Fahrenheit. But if you add ice and salt together, it will lower the freezing point down to as low as 16 degrees Fahrenheit. In other words, the molecules that are making up the water, when they are in the presence of salt, will remove more thermal energy from those molecules and slow them down even more so that they are vibrating even more slowly when they are locked into place in their solid structure. It also means that when we are looking at all three of these pieces of the puzzle, the can, the salty ice, and the air, the ice has the lowest thermal energy, followed by the can, which has a medium amount of thermal energy, and then lastly, the air, which has the highest amount of thermal energy. So the first thing that I focused on was the interface or the place where the ice and the can connect. So where we have the aluminum can and the ice coming into contact, that means that the molecules are also coming into contact. Because the aluminum molecules have a higher thermal energy than the ice molecules, thermal energy will transfer from the can to the ice. This results in the temperature of the can going down and the temperature of the ice going up. The ice would therefore begin to melt when it is in contact with the aluminum can. And if you've ever held an aluminum can that has ice in it, you know that um, the aluminum can is going to feel cold, really fast. In fact, it can get so cold, it can even burn your skin. The other thing that I decided to focus in on was the interface between the can and the air. Once the salt and the ice have been inside of the can for a while, a significant amount of thermal energy has left the molecules in the can, therefore lowering the temperature of the can significantly. So that when air molecules are colliding with the can molecules, thermal energy is being transferred. And thermal energy gets transferred at a faster rate when there is a greater difference in thermal energy. So the oxygen and nitrogen molecules are going to bump into the aluminum can, but they have such a lower freezing temperature that they still stay a gas. And that's one of those properties of matter. However, with the water vapor, physical property of water is that it will freeze at 32 Fahrenheit. So it does not take much removal of thermal energy to make that water vapor freeze. So this is similar to what is happening when frost forms on our cars in the morning or on our windows as we start to get into wintertime. And it's also very similar to what happened to the popsicle. So I'd like you to think about what is said here and then try to apply it to the popsicle and make sure that your model has got similar elements to it when you are explaining the popsicle. Good luck, scientists.